So that's the answers one. That's without the answers. Hello, people from YouTube. Welcome. We're gonna be doing an reasoning and logic end term exam. Just to see how we're going. Okay. Now can I close this? Yes, I can. Oh, sick. Final grade computed as a thing. Cool. Sick. Okay. Word. I'm also gonna open my OneNote because they're actually, let's not use Word. Let's use Overleaf because uh, homework. New file. What's in exam.txt. Okay. A little bit claustrophobic. Not gonna lie, but that's alright. Let me just copy over the header and the footer real quick. I didn't do like any preparation. I just decided to just go do it. So sorry if it's a little bit unprepared. Okay. So let's say question 1. And let me see if I can actually find it on the paper. There it is.
Where are you streaming this, by the way?
Hmm?
Where are you going to stream?
That's a good call. I was like, wait, why is it not streaming? But that's because I didn't press the stream button.
Okay.
That might be useful.
Yeah. Okay, so now I'm streaming to YouTube, not streaming to YouTube, but like I'm recording for YouTube and streaming. Okay. So first we're gonna have some multiple choice questions. Not gonna be too much latex involved there, so you're probably still good for now. Okay, so which of the following claims cannot be true for sets A and B? The power set of A is a subset of A. A is a subset of the power set of A. A or 1 is an element, or A, the union of A and 1 is an element of the power set of the union of A and 1. And the union of A and B is an element of the power set of A union the power set of B. Okay, let's see. So it cannot be true. So if we have a single way to make any of these true, then we know that that's not going to be the answer. A being a subset of the power set of A. So let's just see if I can find, because is this one open book or not? Oh,
I don't think so.
This one is closed book, so we're gonna be. Well, actually, what do you guys think? Should we do it like open book? Should we like?
Fuck it, we're learning, right? I mean.
Yeah, exactly. Plus, we're gonna yeah, we're gonna have this book eventually, anyways. How do you spell power set? Oh, like this. I see. So A being a subset of the power set of A.
Yeah, B is definitely possible.
Yeah. However, I'm not sure about A. Like the power set of A being a subset of A.
I don't think it's possible.
No, I don't think so either. I was thinking maybe in like the edge case of the power set of an empty set, but even then, the power set of the empty set is the empty set. Wait, no, then it would be true.
Yeah, then it would be a subset of an empty set.
No,
Yeah.
the power set of the empty set is a set of an empty set, so it's not right.
Yeah. So in that case, wait, so the power set of an empty set is an. So this is a set containing the empty set, and this is
Yes.
just the empty set. So that's not
Right.
true.
Mhm.
Okay, so in that case, A is indeed not like being able to be made true.
Yeah.
Yeah.
Yes.
I guess you can think of it in the way that the power set will always have like uh more brackets in a
Yeah.
certain sense.
Yeah, indeed. Because like the power set of anything will contain that set
All the
in
possible
itself.
scenarios. Yeah.
Yeah.
So we can like for example say for a fact that if we have the power set of a set containing an element A, that will be I don't know a set containing the set of with the element A, but also an empty set. Like if this
And
is
some other things as well.
yeah some other things as well. But like the um yeah, so there will always be like more brackets in the power set itself than the actual set itself. So
Mhm.
I think A is cannot be true. So 1 is A. 2. Sean and Michelle solve different crimes. The predicate logic is most accurate. So we have Sean and Michelle. Crime X of crime. Solve X Y X equals Y. Whew. Okay, so translating these would be there is an element which is a crime, and Sheen solves that one crime, or Michelle solves that one crime. Well, that's not saying anything about being different. And the same thing is for here. Like here it says for every element, if X is a crime, then if S solves it, then M solves it. So in that case, they would say all the crimes that S solves are also solved by M, which is also not the case. Um, there is an X and there is a Y, for which X is a crime and Y is a crime, and X is not Y. So this part means there are two distinct crimes, for which M solves the first and X solves the first and M solves the first, and X solves the S solves the second, and M solves the second. So this says there are at least two crimes that are solved by both people. But that's not true. Oh, it says there are several different crimes, so even if it will be true, then I mean, Sean and Michelle solve several different crimes. So this says there are at least two crimes that are not the same that are solved by both Sean and Michelle. This one might be it, but we'll look at the next one. Um, ooh. For every X, X is a crime, and there exists one Y for Y is a crime, and the rest is the same. So, I can already give a counterexample for this because I am not a crime. So, for if you have like,
I mean, that's not what it says, to be honest. You don't want it to told you here.
hmm,
Because it doesn't matter if it's a. Like,
well, I mean, it does. It's indeed like not. It doesn't matter if it can't be true. If the sentence says so, then yes. But here, this statement itself, like we can ignore the second part because it's an and. We can say for
oh,
every
okay.
X, X is a crime. Well, that's not true because Sean is not a crime and Michelle is not a crime, and that's explicitly said here.
Okay, I get what you mean, okay.
Yeah. So I'm quite sure this is C. By just going over them. However, if this said like if the sentence was everything is a crime and there are other crimes which are both solved by Sean and Michelle, yeah, it still wouldn't make much sense because Sean and Michelle are not crimes. I don't know. Okay, consider the following argument. If A is a subset of B and B and C are disjunct, then A is part of B and C. Or B, is a subset of B and C. What is a counterexample to this argument? So, a counterexample for an argument means both of these have to be true and this has to be false. So, A is a subset of B. Oh, my bad. I thought this was disjunct, but this means is not disjunct because there's a stripe through the thing. My bad. So B and C share at least one element. Okay, so A is a subset of B, which is the case here, and not the case here. So this one already falls out, and it is the case here. So C is already not correct because then this wouldn't hold. See, the union of B and C is other than 0. Well, that makes sense because in all of these it's other than 0.
That's intersection, not union.
Oh, my bad. The intersection. Yeah, union is with a U, so yeah. I'm very bad at terminology. If I make mistakes like this, please correct me because I am very, very bad at terminology. Okay, so the intersection of... okay. So A is a subset of the intersection of B and C. So we need a case where this is false. So we need somewhere where A is not a subset of the intersection of B and C. Well, in that case, this one, I think this one would be a proper this example or a counterexample, because the intersection of B and C is only the elements that are both in B and C, namely 1 and 2, and A is 1, 2, 3, which is not a subset of just 1, 2. Let's see if the other ones are correct. So A is a subset of B, and because it's not a proper subset, they can also just be the same, which is correct. And B and C are not disjunct. So there are elements in B that are also in C, which is also correct. So the answer here for 3 is B. Which of the following functions is not well defined? Okay, then we open this one and we go for... oh, bugger off. Well, what is the official terminology for well defined? Does that mean that there's like not an output for an input?
Yeah, it's just that every input has an output, right?
Yeah, it could be.
Probably it would
Well,
just mean that if it's not well defined, then it's just not a function. So maybe there's just an argument
Oh
that
yeah,
doesn't have
because
a value
which of the
or
following
something.
function? So if it's not a function, yeah. Um, so what are properties again of functions? Functions have, for every input, they have at most one output. And I remember that because like the function f of x equals plus or minus x is
And at
not a
least one
proper function.
output as well.
Hmm?
And at least one output as well.
Yeah, so they have exactly one output.
Yes.
Well, not at least one output, only one output. If it has multiple outputs for one input, then it's not well defined.
Yeah,
No,
well,
he
I
said
said
that.
at most one output. He said at least one output. So together that's like exactly one output. So every real number, yeah, you can round every real number up and divide it by 2. That should be fine. Every natural number, yeah, this is just an if else. Natural number times natural number to all the integers. You can have, yeah, because this can be a negative number that will just be a division. Wait, I think it's B actually. Now that I look at it, because if we have, let me get some maths involved. If we have n equals, I don't know, 2, m equals 3, or let's say negative. Oh wait, because they're never mind, because they're natural numbers.
Yeah.
I was about to say, because if you have done a negative number, then it would be like 1 divided by, but that's not the case. Yeah,
Yeah,
and
I think maybe C, one of the outputs may be like a natural number, but not rounded to an integer. So maybe
For this
that's
one.
one case of that. No, for C,
Well, C
maybe
does
there's
like
not a rounded number or something.
well, C takes as input takes a natural number, so a number 0 and up, and it outputs to all the yeah, all the integers. So yeah, with 0 it would be 1, with 1 it would be -1, with 2 it would be 3, with 3 it would be -3, 4 it would be 5, with 5 it would be -5. So I think that's just
Okay, never
all
mind.
valid.
So actually, the answer is A, and the reason is because if m is 3, then we don't have a value.
Yeah, yeah, yeah. Oh, that's pretty nifty. That's smart, thank you. I didn't think of that. Yeah, of course, can't divide by 0, makes sense. Okay, cool. Consider the following templates for proof by induction. Which one does not prove their claim over natural numbers? Notice the claim differs from... Okay. Um, oh, I was really confused about this notation. I was like, for every n that's bigger than 5p of n, but that's just for every n that's bigger than 5, then p of n.
Yeah, they could have like put a space or something.
Yeah. Okay, so I know for a fact that this one holds, because the counter positive of this is just p of k implies p of k of 1, so that's just the default proof, the lowest number. If that holds, then the next one. So this one is holds for sure. Um, if we replace k by k plus 1 here, or k minus 1 here, then this is just p of k implies pk of 1 for all of k is bigger than 0, so this one holds too. This one holds too, because this is just all even numbers, so yeah, that makes sense. Yep, B is wrong. Because if you prove that this holds for all k is bigger than 5, then you cannot use that to induct something on less than 5, and the base cases are less than 5. So if this had proof p of 5 and this, then it would be correct. But because we only prove that this holds for everything greater than or equal to 5, we cannot use these base cases. So if this said holds for all k greater than 3, then we could from there deduce that 5 also holds, and there on that will work. But yeah, because this starts at 3 and 0, then yeah, this couldn't hold in any way. By the way, if at any point you have any questions, just stop me. Which the following cannot be used to show that two propositions are equivalent. Show that this is a tautology, so this is the same as p x or x, or x north, like the double arrow, right left arrow, which is indeed showing that it's a contradiction, or are equivalent. Excuse me. B is a contradiction and not Q is a tautology. Well, yeah, then they're both just contradictions, so that's also fine. This here is showing that P implies Q is... Oh, wait, contradictions. So here you're saying P implies Q is false and P is true, but that doesn't mean Q is true. So I'm leaning towards this one. Let's look at what C says first. Well, yeah, by the I don't know if there's like a law for that, but like because the implication sign is transitive, P implies R and R implies Q is the same as P implies Q, and here it's just saying then P implies Q and Q implies P, so that's the same as saying this one. So these are correct, this one is correct, and this one is wrong. So that's B. You guys agree?
I'm not sure the converse is logically equivalent
For which one?
for C because it's Q implies P, not Q implies not P.
Well, for C or for D?
C.
Okay, well, let me work it out real quick. So we have B right arrow R and R right arrow Q and Q right arrow B. So we have this. Let me scroll a little bit to the right, recompile. Okay, so we have this. This is the same, this is logically equivalent to saying that P right arrow Q and Q right arrow P. So, yeah, this is the same as saying this. And that's the same as saying P left right arrow Q. Oh, let me put an enter there. And this is the same as saying these two statements are equivalent. Because if this is 1, this is 1, and if this is 0, this is 0. And in the case of C or B, we have by the contrapositive, we would have B, or we know that this is a contradiction, so I'm going to add a negation sign in front of it. P right arrow Q and P. So this is what we know for the second thing. And if we know that P is always true and P implies Q will be true, then we know for a fact, okay, Q is also always true. Or even then.
We don't know that because
Yeah, we don't know that. So this, even if it would be true, then it still wouldn't hold. But we say that this isn't true. So yeah, this also doesn't hold. So B is just a bunch of baloney. Okay, do you understand like this part? Like the this part? So like the
I guess for B you could show like a counter argument to show that it isn't a tautology.
yeah,
I mean equivalent, it isn't equivalent, yeah.
yeah, it just these are just by definition not equivalent because equivalent is something else than what they're saying there. And we don't it's not an open question, so we don't have to say or prove anything. Oh, we're not done with stepping yet. Yeah, okay. Consider the following informal description of relation R. R is a binary relation from the set A to the set B in such a way that every element in A has a relation to exactly two unique elements in B. So there we would have so every element in A has a unique relation with at least that to exactly two items in a set B. Well, I think the answer is D, because this is like not true in any way. This would just create the set 0A, 1B, 2C. Or, that's not... Wait. Help me real quick. Would this create the set 0A, 1B, 2C, or would it create the set 0A, 0B, 0C, 1A, 1B, 1C, 2A, 2B, 2C.
Wait, what is your question?
Okay, so for A we have R equals to A times B. Let me grab my 1 real quick. A times B. Like, would that be the same as saying, like, A, for every element of A you create a relation with every element of B? So it's just like saying 0A, 0B, 0C, 1A, 1B, 1C, 2A, 2B, 2C.
Yeah.
Okay, cool. So then that's not true, because
think.
that would create an element from every element of A to 3 unique items in B. This one doesn't make any sense either, because it just relates stuff to from A to A and from B to B. And every element from the set A has a relation to exactly 2 items in B. So yeah. Yeah, no, I think this one is correct. Because every element in A, 0, 1, 2, has a relation with exactly 2 unique items in B. So 0A, 0B, 1A, 1B, 2A, 2B. Where it's, 2 unique items in B, they just mean, yeah, okay, they mean that it cannot be the same. Or does that mean that for every element there have to be 2 different items? So like if 0 is related to A and B, then 1 has to be related to like not A and B, so like B or C or A and C.
Well, that's not one of the options in the multiple choice, so you don't
Well,
think
I
so.
mean it is, because this one A is related, or 2, excuse me, 2 is related to A and C, 1 is related to B and C, and 0 is related to A and B.
I think it just
Yeah, but
means
that's the
that.
relation from B to A, not from A to B.
Yeah, but it says in such a way that every element from A has a relation to 2 items in B.
But it says 2 unique elements and not like uh, a unique set to like of 2 elements or something like that.
We'll say B and we'll see if we're wrong. Okay. Consider the argument if A and B then C, or A and B therefore C. That's the real way to pronounce this. Which of the following methods can be used to prove the validity of this argument? Show that A implies C is a valid argument. I don't think that's correct. Show that not if not A implies B, then not C is a tautology. Well, the thing we want to prove is that if A and B, then C. So that's not quite true as well. Use equivalence rules to derive that A is equal to B, or A is per definition equal to B, and B is a tautology. Well, I mean, if these are both tautologies, the only way to prove a counter argument, or to disprove an argument, if it is that both of these are true and this one is false. This one just says these two are always true, but this one can still be false, so that's not correct. Construct a truth table for A, B, and C and inspect all rows in which C is false. The argument is valid if and only if both A and B are also false in those rows.
Well, no, they don't have to both be false.
Yeah. Like, if one of them is false, then it can be that...
Yeah.
Let me think real quick. So if we have the negation of A right arrow B, that is the same as saying the negation of A or B, and that's the same as saying A and the negation of B. Yeah, but it doesn't make any sense either, because then it would say if not or A and not B, then not C. But yeah, this one doesn't make any sense.
I think it's A.
This says that if A is true, then C is true.
Yeah.
I mean, that's only part of the argument, right? So that
I
doesn't
mean,
prove the whole
if you
thing.
know that, if you know that it's true that if A is true, then C is also true, then it doesn't matter what B is, and it that means that if A and B are also true, then C must also be true. I don't know how to express this, but
Yeah, I think A seems the most logically solid argument here out of everything. Like, everything is false, and A is at least pushing into the right direction, so it might be correct.
Yeah, I mean, it's only missing like the argument if B therefore C. You would need to prove that as well,
not really, because if you
right?
know that A always, I mean, if you, fuck, how do I say this? If you know that A implies C, then you know that A and something also implies C.
But it can still be false, and the argument could still be true, right?
Oh yeah, but yeah, okay. So I see what you're trying to say. So if A is true, then C is also true. We know that from this. Um, so that therefore the only way to disprove an argument is that both of these are true and this one is false, and that's impossible. Because if A
Yeah,
is true, then C is also always true. That's what we have shown.
yeah.
Yeah, that makes a lot of sense. Okay. You guys understand what I just said? I'm gonna take that as a yes. If you have any questions, let me know. Okay, which of the following claims about sets ABC is always true? So we have the intersection of A and B union C is always bigger than or equal to A, yeah, of course, the cardinality of. It's always bigger than the cardinality of A intersection B union C. Well, this doesn't have to be true, I guess. Uh,
What the hell is and or?
um,
I guess it's just an or, just to
yeah, it just
differentiate
means
from an
one of these
XOR.
two has to be true.
Yeah.
A union B is, or A union B is always bigger than A. This is correct.
No, because A and B can be the same thing.
Oh, it says bigger. I thought it said bigger and equal. Good catch.
And if A and B are the same thing, then both of these are false then.
Yeah, because they say greatly bigger. So yeah, that's correct. My bad. A intersection. Yeah, in section B, greatly stricter or equal to. Yeah, greatly bigger or equal to the cardinality of A union C if the cardinality B is greater than the cardinality C and cardinality A is bigger than 0. There's at least one element in A, and there are more elements in B than there are in C. Well, no, this is the intersection, so it could just be that there's like one element in A, 5 elements in B that are all disjunct, so this will just be 1, and 2 elements in C that are both part of A, so this will be.
It could also just be that A is an empty set.
No, it couldn't because A is
Oh
always bigger
no.
than 1.
Oh, because there's an if.
Yeah, but
Okay.
I'm thinking because. No, I don't think that's true. Because this will at least be the cardinality of. Oh, wait, no, this is the union. Because if these two sets are disjoint, this will be 0. If there are 2 elements together, then this is 1. Yeah, no, so this is false as well. Because this is not true for all sets. But, this also doesn't make sense. Because they use if and only if, so that means that these are exactly the same. Um. Hmm.
What's the issue?
And I'm not sure which one of these is true because they seem to always be false.
It seems like A because like B, C, and D seem to be false, but I don't know.
No,
Yeah.
it's not A because if A is empty and C is really big, then it would not hold.
Yeah. Indeed. Okay, so this one we know for a fact that this is false
Are
because
you
we have
sure
given an
it
actual
wouldn't?
counterexample.
Are you sure it wouldn't hold in A?
I think so. Because this is either in this or in this. So if this is really big and A is
Yeah.
empty, so this will be 0 or really big. So this will be really big.
Yeah.
Oh wait, but this is bigger than.
Wait, if C is empty and A is really
Yeah,
big.
okay, I was about
Yeah.
to say.
Yeah, okay, yeah,
Okay,
sorry.
C is
I fucked that up.
empty or A is really big and there are no elements in A that are in B. Then this will be 0.
Yeah.
And that would have to be bigger than. And then just,
Actually, wait. If C is empty, wouldn't this just make it equal? Because you would just get A and B in both.
Yeah.
So I guess we could try and translate to propositional logic. Probably that would be
Yeah,
the
let's do
easiest way
that.
of proving it.
Um,
I mean, on an actual test, you wouldn't do that because it takes time, but we can do it here, I guess.
um, so let's create some predicates. Well, this is only for checking, so it's like usually you would say x in A or and x in B. Oh, actually, fuck it. Let's do that. Let's do that.
Yeah.
And then we'll say or x in C. Okay, compile. So we have x in A and x in B or x in C. Then I can take my very nice notes here and see that by the distributive law, we can say that, let me add some slashes here, we can say that this is equal to x in A or x in C and x in A or x in B. Let's see if that's correct. No, this is not correct. This should be x in A or x. So this one gets distributed to there, so this becomes x or A or x or B. And if it gets distributed to there, so that's, yeah, okay, that's correct. And then what happens next? What do we want to get again? We want to get A and B or C.
Yeah. So we have something pretty similar to that.
Oh wait, wouldn't this be part of the absorption law?
Because like that might be the case because the right side, like the B or C, is the same as like in the other expression. And then we have something that's bigger than that.
Yeah. So,
Wait, what was the absorption law you said?
yeah. Let me actually look up.
I never remember those laws.
Absorption law is P or PNQ.
Yeah.
Hmm. Wait. Uh.
Can you show like a list of the laws or something?
There is a list of these laws in the book. Oh shit.
Ah,
I just have that on my second monitor. I can't share these because that's not allowed and stuff. Blah blah blah. This is my old thing. I don't need this. Um, okay, so I need this. I need PDF viewer of this one. I accidentally closed everything, so I have to open stuff again. Give me a sec. Okay. So absorption law and sets. Yeah, I was just there. Okay, so the theorem is indeed A or A and B equals to A. And A or B. So
I guess we could like prove this from this, because if you think about it, if we compare it to like the uh, to to the expression on the right,
yeah,
for it to be true, I don't know how to explain this. But if you look at the expression, it it would be so much easier if I could just write this down.
yeah.
If you have
We
x is element of B or x is element of C, we also have that on like the right expression, and then we have an and so uh, for an element to satisfy the expression on the right, uh, it needs to be in A, but in the expression on the left from what we have got here, it can be in A or in C. So it makes sense that the expression on the left is bigger or equal to the one on the right.
yeah. That's honestly like we don't have to prove any of this because
Yeah.
it's a multiple choice question. We'll just say A. Let's go.
True.
Okay. In his TED talk, What Do Top Students Do Differently, Douglas Barton claims that in our research we found that hard work was a necessary condition, but it wasn't a sufficient condition to doing well. Um, Working hard, doing well, it's following is true. Well, then we open our RNL book. We go for can I spell necessary? Um, Necessary, page 12. Um, I want page 12.
Necessary is the one on the right.
Okay.
The same.
So where is that? Sufficient? Which one? Like I know that necessary is right arrow, sufficient is left arrow, but I want to be able to find it in the book. Wait, left, right arrow, left, right arrow, right. So this is sufficient.
Yeah.
Yeah, and the other way around is necessary. So by this, we say that so let's see. It is necessary, so that is P, so that is working hard is left arrow of doing well, but not that left arrow looks so fucking cursed, man. I just can't look at it properly.
So
And
why
not
do you
be.
write it like that?
Hmm?
Why do you write it like that without using like? You could just use a right arrow.
Yeah, if I just flip the arguments around and say Q right arrow P.
Yeah.
So this is what we want to prove. You want to say Q right arrow P and not P right arrow Q. That's not what this is. This is like the other way around. And this is exactly what we want to prove because the contrapositive of this is P implies Q. So here we have not Q
Yeah.
implies P. So here we have not P implies Q and Q implies P, which is what we have here. So then we can say that this is C. How many questions does this thing have? Whew. 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 Okay. 11. Following claim over all natural numbers. For all natural numbers n, if 4 divides n, or 4 divides, if 4 divides f of n, or 3 divides f of n, oh wait, there's no if. Oh, excuse me. For all natural numbers n, 4 divides f of n, or 3 divides f of n. With some function. Okay, so this one would prove that 4 divides f of n and 3 divides f of n, because in that case 12 would divide f of n. This here only says that if f of k does not divide 3, then it divides 4. But then it could also just be the case that... Actually, this might be true. I'll look back at it later.
Which one do you mean? B?
Yeah, B.
B looks right.
Yeah, I was
Yeah,
about to say,
B is
because
right.
like... not x implies y. That is the same as saying not x or y. So that's the same as saying x or y. So that actually looks pretty correct. And here it says if 2 divides k, then 4 divides f of k, and 3 divides k, then 3 divides f of k. But, 1 doesn't divide either of these. Neither does 5, neither does 8.
Yeah.
8 does, but I meant 7. You get the point. So C doesn't hold. And here it splits it up to cases. So when k equals to 2m... Wait. Is not suitable.
Yeah.
Okay. Yeah, no, okay. So then the answer is C.
Mhm.
Yeah, okay, cool. No. 'Cause, like,
Indeed, they didn't.
I
even
thought
say
I thought it said suitable. I was like, huh? But yeah,
What
this
exactly do you
this
mean by
proves
not
this and
suitable?
also some other stuff. This proves
D
it.
is-
This
B
proves it
is
and this
kind
proves
of
it.
bad as well. I mean, it's good, but they forgot to say that m is a natural number.
Hmm?
Like they didn't say in D that m is a natural number. That m is a natural number in D.
Yeah.
But
Well, I mean, since k equals to 2m, we know k is a natural number. Therefore, 2m m is also a natural.
oh yeah, that's
Yeah.
yeah, I guess true. No, not necessarily, because it could be that m is 2.5, and then
Yeah, but
k
in that
is
in that case, we can have this case.
But I guess we can assume we know what they meant. So yeah.
What exactly do you mean by not suitable?
That it
That is
doesn't
not
prove-
like if you prove what is written down there, it doesn't prove what is up there.
It's if it's suitable, it means that it basically proves it.
Yeah.
And if it's not suitable, then it's bad. That's basically.
Yeah. So basically, it's if you prove this, then you prove this. But in this case, for C, if you prove this, then you do not directly prove this because you also need to do some extra work showing that all the other numbers also do this.
Yeah.
But how is A suitable? Because like if f of k is 8 or something, then it is divisible by 4, but it's not divisible by
No,
12.
but here you prove that all numbers are the output of all numbers is divisible by 12, and if it is divisible by 12, it is also divisible by 4 and 3.
Yeah.
Oh, so it's
Because
just a
in-
bad proof.
Yeah,
Yeah,
this
and
is like this proves this, and not only does it prove A or B, it also proves A and B because every
Yeah.
number that's divisible by 12 is also divisible by 4 and
So
3.
what you-
But
what
it
you're-
also improved like this one because the case where both are true is also included in the OR statement.
Yeah.
So it's basically just not a contradiction, but it doesn't prove everything.
This one proves it, and more. So this one is alright to prove this, but it's just not the way I would do it. This one proves it because, you know, if it doesn't hold for this one and it holds for this one, that means it holds for either one. This one splits it up into cases, showing that, like, in the case it's odd, it's this, in the case it's even, it's that, so that also covers all cases. But here it only proves that if k divides 2, then it's this one, if k divides 3, then it's that one, but k can also not divide 2 or 3. Namely being 1 or a prime number that is not 2 or 3.
Yeah, okay, nice.
Yeah. Consider the following formal structure S with domain PEMFG. Which of the following claim is true? There exists an element x, for which L of x, so x is either one of these three, and every y, for every element y, w of this one of these elements, comma y.
Okay, so it's already false because there's no PP.
Yeah, exactly. There's no pp.
Yeah.
Well, I mean, it would have to have either pp, aa, or gg, and it doesn't.
Yeah.
Okay, here for every element of x, if L of x, so if x is either p, a, or g, then
no, because no.
Yeah.
Sorry.
So if it is L of g, then there exists a y for which b of x comma y and y x is not equal to y. So does p have an element here that is not the same? No, the only thing in here with wait. Yeah, okay, so we don't know that this is equivalent, so we don't know if a of p then also p of a. We don't know that, so we can't assume that. So in this case, we can say, okay, p does not have an element that is not p and also is related to p. And the same goes for a. Well, a does have one, and g
Yeah, but
does.
we haven't for all, so yeah.
Yeah, exactly. So yeah, because p and g both don't have it, you know, it's counterexample, so this is false. Okay, so then for all x, if x is in L, then x is in P. No. Oh, or if x is in P, then x is in L. No.
I think it's just no.
Come again?
What a free example.
So if we say, okay, let's take the letter P. P is in L, but it's not in P. So this is false. And it is... Oh, wait. No, wait, this is 0, 1. So that is... Oh. 0, 1 is not necessarily a counterexample. So this would be true. So this would be 0 or 1, which is true. I think this might be true.
What do you mean 0, 1?
Okay, so let's take an element. Let's say P.
Yeah.
For all elements x, that is, and we know for a fact that all elements x are either these three or these three.
Yeah.
We can say, okay, is it in L? Yes.
Oh, okay. No.
If
Oh,
this
wait,
then
so
that,
it's
yeah,
not
that's not
necessary.
true. But it's this thing that is false, or if it's in there, then it's in there. Well, it's not in here, so that's a 0. Implies not it is in there, so that's a 1. 0, 1. That's allowed.
Yeah.
So this is
Oh,
0
so
or
it's
1.
basically just proven by the fact that for every element in S, it's either not an L or not an P.
Exactly.
Yeah.
So that is C as well.
Isn't, by the way, like P implies Q or Q implies P a tautology?
Let's find out. So we have L right arrow P. I'm using lowercase letters, whatever. Or P right arrow L. Okay, this can be rewritten as... Oh yeah, definitely. Oh, this is like the most easy example of a tautology if you would see one. So this can be written as
Well,
not
the most
L
easy one.
or P or P or not P. Oh, sorry, not. I'm using not neg. I'm using not. I should be using neg. Neg P or L. So Yeah, this is just saying the same as and in here, not L or P or not P or L, and recompile. Oh, I forgot to take away bracket. Then we can reorder this a bit, so we can say not L or P or not P. So this is literally. Oh.
Yeah.
Yeah, this is literally just true or true. So a contradiction or a contradiction, which is a contradiction. Or a tautology or a tautology, which is a tautology. Yeah. Okay, sick. 13. Consider the following recursive definition of a set of strings, words S. A is in S. If X is in S, then XI is in S and AXA is in S. If X and Y are in S, then IXI is in S. Nothing else is in S other than the strings constructed by these rules. Okay, which of the following claimed over the set have false? All words in set have at least one A in it. Well, that's correct because everything gets built up from this. There is a word in the set without an I in it. Well, yeah, that's true as well. This one. There is a word in the set with exactly 5 A's in it. Yes, namely if you have.
Wasn't this one on the presentation as well?
It could no. They do use a lot of string building notation, but I don't
Yeah.
think this exact one was on there.
No, I'm pretty sure Stefan covered this as well.
Oh yeah, it could be. Well, I'm rounding it up real quick. It's not that hard of a proof. There is a word with exactly 5 A's in it. Well, A is in here. If it's in here, then A is in here. If A is in here, then A is in there. So that's C. And all words in set have an even number of I's in it. Well, A is in here, so AI is in there, and that only has one I, so that's false.
Yeah.
Consider again the recursive definition. Okay, we're done. Which of the following rules should we add to ensure that string MIA is part of the language? Well, this one is not correct because there is no way to just create IA. We can only create AI. So with only this rule, then we would have the thing MAI in a set, but not MIA. Okay, here we say I is in a set. If X is in a set, then XM is in a set. Well, that's not going to help us because this will put the M on the end, and we want the M on the front. Okay, we say M is in a set. If X and I and Y are in a set, then XIY is in a set. This one looks pretty good because we have an M in a set, we have an A in a set, because of the rules 1 and 5. Therefore, we will have MIA in a set. So this one is it. So we know it's C. And then for the last one, M is in a set. If they're in a set, then IXY is in a set. Well, we don't want IXY or IMAM. We want MIA, where the I is in the middle, not on the left. So it will be C. Okay, figure 1 shows a Venn diagram. Which of the following sets is represented by the shaded area? So you have the symmetric difference of A and B, union the symmetric difference of C and B. The symmetric difference, that is an XOR. So that means it's this part, union this part. So no, but that's not true, because then it would only be this part, and this part. Okay, everything that's A that's not in B, so that is this part. Union everything that's in C that is not in A. So that's this part. So these two. This
Yeah.
might be it.
Yeah, that's true.
Makes sense.
Yeah, so it's like this part, union this part, is equal to this whole thing.
Yeah.
Okay, so this one starts out with everything that is not in A So that is this whole part minus everything in B. So that's only this part.
No,
Union.
because it's even more because you also get
Oh, the outside.
Outside as well.
everything outside as well. Yeah.
Yeah, so I think this.
There's no outside.
Yeah, so because of that, we already know this is not going to be it. And this is everything that's in C and not in A, so that's this part. And that the intersection with everything that's in C and not in B, so that's this part. So like these two and these two, so that's only this one. Is that correct? Yeah. So the intersection of this one and this one is just this part. Or the symmetric difference or A and B, which is this part and this part, but that's also not true because then it would also have this part on. I'm using a lot of this parts, I'm sorry for that, but yeah, we already got to the point where we know it's B. Okay, Turkish world, let's go!
You mean Duck's World?
Hell yeah. Consider the following alternative visualization of sets A duck empire. The set P contains all ducks that are within a distance of 2 from the circle. Q contains all ducks within a distance of 2 from the star. R contains all ducks with a distance from 2 from the square. Ducks cannot travel diagonally, so the center is exactly 2 squares away from the square, with a distance of 3 away from the star. Let's look at that. So this one is 2 away from the square and 3 away from the star. Yeah, makes sense. So, let's actually create these sets real quick. P is that are within a distance of 2 from the circle, so that's only... Yeah, we can get to this one and we can get to this one, but not to this one. So let's label them A, B, C, D, E. So this is the set of A and B. And Q with a distance of 2 from the star, so that is 1, 1, 2, 1, 2. And that's it. So this is B, C, and E. And R is distance 2 from the square. So that is R equals to this one,
Which
this
one
one,
is
this
E?
one, and that's it. So that is A, D, and E. Which of the following claim is true? The union of Q and R is 5.
Why is E and Q, by the way?
Hmm?
Why is E and Q?
E and Q. Q is this 2 from the star. We have A, B, C, D, E. So that's this one.
But it's a distance of 1.
Yeah, but it's within
It's
a distance of
within.
2.
Ah, okay. Right.
Okay. So, the union of P and Q is 5. Well, that would be wrong because that would mean that everything
No,
is in
that's
P and everything is in
intersection.
Q.
That's intersection.
Yeah. Sorry, the intersection. The cardinality of P plus cardinality of Q plus cardinality R is 5. Well, that's not true either because... Yeah, that would be like 2, 5, 8. The cardinality of P, R times R matrix multiplied by P. I don't know if that's like what it's called, but whatever. Well, we know here that the cardinality of A matrix multiplied by B is A times B. So that would be...
Cartesian product or something?
Hmm?
Isn't that the name of that like the Cartesian product?
Oh, that could very well be. Yeah, that's... I don't know what it was called, but I've heard the name before. So that's like... I'm just called that thing, like the blah blah product.
Okay, I googled it and I think it is.
Yeah. Cartesian product. And then that leaves it with only one answer, which we already quite know it's correct. The union of Q and R is 5. And we know Q is ACE, BCE, and then ADE. So that would be A, or let's start from Q. So that's B, C, E, A, D, E. But because there can only be one element of every set in the set, that's just this. I thought it said bread for a second. But yeah, we have beside. So we know that this is B.
B.
Okay, next one. How many questions are there again?
26.
20, 26.
shit.
Oh, we're only busy for how long? Like an hour and 4 minutes? Okay. Which of the following statements is true? in a real test, I wouldn't do it like this, but I'm going over every single answer of every single question, to make sure that like the people at home or the people watching this back know for every single answer. Okay, so the power set of the empty set is the empty set or a set containing the empty set. I think this one might be true.
Yeah.
Yeah, because the empty set or the set containing the empty set will be all elements in this set, which is nothing, or all elements in this set, which is the empty set. And this will create the set containing the empty set, which is the power set
Wait,
of B.
actually, no, it isn't that because the power set of the empty set. Oh wait,
It's an empty set containing the power set.
doesn't it also
Yeah.
Wait.
Oh,
Oh yeah, you're
I
right.
think it's an empty set and a set of the empty set.
So B is correct, right? Yeah.
Okay, wait. Let me write this out. So the power set of the empty set, I'm just going to call it a 0, is equal to a set containing the empty set.
Yeah.
So we already know A is wrong. We can now try to construct an empty set or this thing. So let's see, that will just be a set containing the empty set, which is correct.
Wait, but wasn't the power set of an empty set and a set of an empty set?
Yeah, that's what I thought too.
Ooh, that is yeah, that is true. So this would create a set of 0 and right?
Yeah,
Yeah.
like that.
Wait, but that's if you do the power set of the
It's
power,
not.
right?
That's if you make the power set of a set containing the empty set, I think.
Yeah.
Oh, I was about to say, why doesn't that work? Power. Oh, I thought it said power low. I was like, what? The power set of.
Bottom there.
Yeah. The power set of the empty set is a set containing the empty set.
Yeah.
The set containing the empty set is not empty, it contains one element, namely the empty set. Woo! Okay.
I could have swear I saw that somewhere. That it's like an empty set and a set of an empty set.
Yeah, but
Yeah,
that's indeed
yeah,
like
yeah.
if it would be
Yeah.
this, like the power set of the set containing the empty set is the empty set and the set containing the empty set.
Which is also the power set of the empty set, which appears in C and D. So
Wait, the
Oh.
power set of this thing?
no, the power set of the empty set is exactly what we wrote.
Oh, yeah. Yeah, that makes sense. Okay, but we know that the answer is B.
But then we also can see quite easily that C and D are false.
Yeah. Yeah, indeed. Okay, so 18. Which of the following claims is false? N has the same cardinality as pi to the power of k, where k is every element in Q. The way I remember this is we have non-zero quite real, which is just, I just think of the number 1, which is non-zero quite real. So n is all the positive numbers or 0. Z is all integer or all positive integers or 0.
It's just all rational numbers, right?
Yeah, all rational.
Here's rational numbers.
Yeah, Q is all the fractions / rational numbers, and R is all numbers non-imaginary. So without an imaginary component.
Yeah. So real numbers.
Yeah, exactly. So we say n is the same cardinality as pi to the power of k, where k is all the fractions.
I mean, yeah, because pi to the k has the same cardinality as q, and we know that q has the same cardinality as n,
Has the same cardinality as what?
as the natural numbers.
Oh yeah. Well, I mean, aren't all of these just countably infinite?
Except for reals.
Real or uncountable.
Reals aren't countably infinite.
Yeah, that's true. So we could say that all of that these three have the same cardinality and this one doesn't.
Yeah.
Yeah.
Okay. I'm gonna look through the other answers as well. So n has the same cardinality as x, where x is 2k plus 1 for some k part of natural numbers.
Yeah.
Well, I mean, oh yeah, we're looking for false. Okay, cool.
Yeah.
Yeah, this is correct as well, because this just stretches it out by a factor of 2 and then slides it over 1 to the right, but it's still as big.
Yeah.
This has the same cardinality as... and this is... No, this is not false. Not true, because this is countably infinite, and all the numbers between 0.1 and 0.11 is uncountably infinite.
Yeah.
So this is not correct, and this is also just correct because it's just, again, stretched out by a factor of 42. So this is C is false. Which of the following?
Wait, but does B not also contain a negative number? So is it still the same cardinality as the natural numbers?
Yes.
Yeah.
Yeah.
Because they're both countably infinite. The only thing that is different from countably infinite is uncountably infinite, and everything not countably infinite. But you get the point. Like, I here have a list of all the things, so I can say the size of n is equal to the size of z is equal to the size of q is not equal to the size of r. And that's because
Okay.
n, z, and q are all countably infinite, and r is uncountably infinite.
Yeah.
Okay, on to 19. Which of the following claims is true? A relation that is not reflective cannot be transitive. A relation that is not transitive cannot be symmetric. Whew. Okay, then I'm gonna go here. I'm gonna look for reflexive properties of relations. So, let's see. I'm gonna make a list real quick. Reflexive.
It's probably D.
Yeah, probably. Ara.
No.
Transmissive.
Transitive.
Transitive. Today I learned. ARV and BRC implies ARC. And the last one was symmetric.
Yeah.
And that one makes a lot of sense. All of them make a lot of sense actually. We have ARB implies BRA. So
It would be better to say that it's equivalent to, not just implies. I mean, you should put like a biconditional because. Oh no, it doesn't make a difference.
I was about to say that it doesn't make a difference. Like here, yeah.
Yeah.
And we also have anti-symmetric, but this one isn't required for something being a equivalence relation. That is if and this is like not written in LaTeX, but I'm just gonna like copy this into my personal OneNote because this really helps.
You're missing a bracket if you're gonna copy it.
Thank you. Okay, so with this knowledge, we will go back to 19. Which of the following claim is true? A relation that is not reflexive cannot be transmissive. Well, that's false. A relation that is not transmissive cannot be symmetric. Well, that's false too. A relation that is both symmetric and transitive has to be reflexive. Well, that's also true. Also false. Yeah, I think so. That's also false. I think D is true.
Yeah, I think so as well. I mean, we can build relations with all of these. So.
Yeah, exactly. It's not like there's some set that cannot be true. So all eight things in these have to be like there has to be a possibility where it's true, or where something has those. Okay.
Wait, so why is it D, by the way?
Because I don't think there's like any constraint that says when it has to have like
None of these relations depend on each other.
exactly. They're all just independent stuff that can all just happen.
What's the rest of D? I can't read it.
Um,
Oh, reflexive. Okay.
yeah.
No,
So
I thought maybe it was anti-symmetric or something. But
no, this is reflection. As Lyra purpose attached for the north, he draws a map of the kingdom of the Panzerbjörn. She also draws the different road between the cities of the kingdom. Lyra's friend Pantalaimon realizes there could also be a visualization of a relation P of X with which of the following statements of the relations are true. Well, it is open thing. It is reflexive, we know that.
Yeah. It isn't symmetric. We also know that.
Yeah. Let me actually like keep this over here as like little helpline. Let's see. It is currently reflexive because everything has a path leading to itself. It is not transitive because you can get from A to D, but not in a straight line from B to C, B to D. And it is not symmetric because then we would also need a line back for everything. Or I mean, these are the roads between kingdoms. So if yeah, okay, I guess they're also symmetric.
No, they're
they're
not.
one-way roads.
One-way roads?
Yeah, that road only goes one way.
Let's assume they're
go
one-way
from-
roads, and if we can't find an answer with that, we'll assume you can just walk both ways. But yeah, let's see. B is not currently transitive, but adding A to C and B to E would make it transitive. Well, that's not true because we would still not have a road from B to D.
Yeah.
It is currently reflexive. Yeah, that's correct. But removing B to C and adding C to D would make it lose its reflexivity. Well, no, obviously, because the only thing reflexivity has to do with itself is just itself, and these two are not related to itself. So it doesn't matter what happened between these, as long as they all retain the fact that they lead to itself, then they're still reflexive. It's currently transitive. Well, this is false because we know it's not transitive. And D is not currently symmetric. But removing from B to C,
This one.
from B to A, from A to D, and from D to C. So then the only thing we would have is from C to E and E to D. And adding from E to C, C to A to C, and D to C. Yeah, okay. So it is D.
Yeah.
And the reason why I'm gonna grab this picture, and I'm gonna open paint.net.
Why not just normal paint?
No, paint.net is my shit, man.
Or Paint 3D.
No, I'm not gonna paint this in 3D. Okay,
You
so
don't
first,
have to, but
Paint 3D is shit.
it is. It
First-
Just use
actually
normal
is.
paint. Normal paint is the best thing.
True.
okay, so first we remove three relationships, namely the one between B and C, B and A and D. Oh, four then. BC, BA, AD, DC. So that one. That's this one.
And DC.
This one. And that's this one. So this is how the map look like after removing all of those.
Yeah.
And then we create arrows going from E to C. So that's like, oh shit, I'm still drawing in white. Let me make it a little smaller again. From E to set a little smaller, miss. E to C. We would add a road from A to C and C to A. So that is easily done. It's just like yoink and yoink. And also from D to E. So it's like this. And then it indeed is
Symmetric.
symmetric because every road going from one to another also has a road going from the other to itself. Dude, I am so good with Paint. It is unbelievable. We had it open in Word. No, we didn't. We had it open in Overleaf. I was like, wait, why is my Word not doing it? So that the answer is D. Oh, I don't want to use the package. Okay. We are currently 1.5 hours into the test and we're almost done. Now on to open questions. Fun stuff. Oh, wow, these are all, oh no. Oh no. 21. A. Create truth tables for both statements. Clearly indicate columns with your final answer and please order your rows containing with all zeros. Starting with all zeros for the propositions. Okay, then I go to homework 1 and I yoink one of those. And this is exam.txt. And this is gonna like cost me some time because usually I would do this in recompile. Usually I would do this in like on paper, or they would give us a way to draw this. Okay, so we have oh god, oh that's not fun. So we need a statement for P goes to R. We need a statement for P, not P goes to R XOR Q. We need a statement for P implies Q. And we need a statement for the whole thing. Then we need a statement for P and Q. And then we need a statement for not P implies Q implies P. And we need a statement for the whole thing. Okay. Then we can say P and Q and R. Okay, and then we can start making our propositions. So I said P right arrow R. So that's one. Then we have the negation of P right arrow R left right arrow Q. Okay, then we have P right arrow Q. And then we have the negation of the opening bracket P right arrow R left right arrow Q logical or P right arrow Q. So that's for the first one. Then we add P and Q. Then we add negation of P right arrow Q. And then we add P and Q or the negation of P Q right arrow P. Fun stuff. Recompile. Ooh, doesn't this look fun, guys? Oh no. Oh no, the truth table is too big for my paper. You cannot
No,
make
it
this
doesn't
shit up.
look like fun.
Hmm?
It's starting to look less and less like fun.
Yeah.
I mean, doing truth tables on a computer is just pain, to be honest.
Yeah, they wouldn't ask this question, so I'm just gonna say insert truth table. Whoa, look, it's a truth table. Oh, dude, we are so good. Are these
Wait, we did have a truth table question at the midterm, right?
Yeah, but then they give like a way to make truth tables, and then they also
Oh.
wouldn't make it this big.
Yeah, okay.
Because like making truth tables by hand is a lot faster than not doing them
Yeah,
by
yeah.
hand. Are these statements equivalent? No, because the row x x has a different value for both, or yes, because every row underneath the final columns has the same value. So these are the two possible answers, depending on if they're equivalent or not. I just couldn't be asked to make the truth table to find out. Rewrite statement 2 to CNF, simplifying the result as much as possible. So CNF is a conjunction of disjunctions. So you start out with the negation of value 1, that is, okay, so you take all values that are false. Then do negation of that row of P and that row of Q and that row of R, or next row of P and next row of Q and next row of R, or dot dot dot, and then simplify out the until at CNF. Let's say let's simplify out using De Morgan's law until at CNF. I would do this, but I don't actually have an expression, so I'm just gonna say how to do it. So we just go down every row and we just do, for example, let's take this one. Let's make a DNF statement of this, a CNF. So we would say not P and not Q and not R, or P and not Q and R, or P and not and Q and not R, or P and Q and R, and then we work out the brackets until we get to like a point where everything is in a form of CNF. Fuck that question. Consider the following properties: the integer 0 up to and including 10. Such number has the property E is even. E if it is even. Okay, I was about to say, huh? It has the property P if it is prime. It has the property S if it is square of an integer. If it is the square of an integer. Two numbers P and Q have a relation if X and R, X and Y have a relation if X times Y equals 42. Describe the structure above formally, give the domain as well as the truth set for the predicates corresponding to the properties and above in a set notation. Okay, so for 22a, that wouldn't be that hard. We just say the domain is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The everything with E is 0, 2, 4, 6, 8, 10. Domain P is 2, 3, 5, 7. Domain S is 1, 4. If it is a square of an integer, 0 squared is 0. So this is something that I would forget if I didn't think about it. But like 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay. Then we have set of two such numbers, x and y have the relation. Then it would make most sense Okay, my question here is, would it be like this? So we could say the set of, let's say, 9 times 10, and also the set of 10 times 9? Or would we say, or a tuple containing 9 and 10, or containing 10 and 9? Or would we say that this is
Probably both of them.
the set of 9 and 10? Because sets are on order, but tuples aren't.
Yeah, but
Okay.
relations taken tuples, I think.
Okay, we'll take this then. Alright, cool.
Yeah.
Can't you just do one of them and say it's symmetric?
I don't... No, I don't think so, because this is like...
That's not the definition, though.
Yeah, we have to give the formal structure. So let's see, 9 times 10 is 90, 8 times 10 is 80, so we'll also include that. 8, 10... Wow, university level maths, guys.
Yeah.
And,
Couldn't you just describe it by writing x, y, and then just saying that x is in the set of 0 to 10 and y is in the set of 0 to 10?
hmm?
Because you're writing everything down, and you could just wait.
I guess I could give like a formal definition where I only have to write down like one of them, but like this is all I have to write down. Or actually, and 9 and 9. These are all the options, so like this is less work than giving like a formal definition of 9 and 10, 8 and 10, 9 and 9, and all the numbers also have their own, their like whatever. Okay.
Okay.
Consider the following extra information for the structure. For every x, if p of x and e of x, then z of x. Can we conclude that there exists an x for which z of x for the structure? Explain your answer in the most 5 lines. Okay, we'll look at p of x, which is this, and we'll look at e of x, which is that. Well, then the answer is, for b, yes, namely x equals to 2. Because we know for a fact that if they're both in p and e, which is 2, because 2 is both a prime number and an even number, then it's in z. So z is a set containing the number 2, so there exists an x for which z of x, namely x is 2. You guys still following?
Yeah.
Okay, sick.
For like the domain, can you say like it's an element of the natural numbers and smaller than like or equal than 10 or something? Or do
I
you have to write
wouldn't
down?
risk it,
You
because
probably could.
if you want to describe the structure formally, they just want everything written out.
Oh, okay. So no like
Really?
set, like they have like the set functions, or I don't know.
Yeah.
Called.
Hey, we did this. Let's go.
Oh yeah, with the 20 proofs.
Okay, so for 23, we need to prove 23. Oh, yeah. 23a. Prove the following claim. To prove. Oh. To prove for all n greater or equal than 1, and in natural numbers, the sum from I is 1 going to n of I times I plus 1 is equal to the fraction of n times n plus 1 times n plus 2 over 3. And now we're going to look at how bad I butchered up that... Oh wait, that looks decent. For all n bigger than 1 and part of natural numbers, the sum of... Okay, yeah, that looks fine. Okay. Well, you guys obviously already know what method we're going to use for this. If you want to prove something for all natural numbers, and it doesn't seem like there's a very easy direct proof. What do you guys think?
Induction.
Hell yeah, that's what I wanted to hear. I'm gonna remove all this shit because we don't need it anymore. It'll be, it's in my OneNote already, so that's whatever. I'm gonna add some backslashes here so it at least looks okay in LaTeX, even though it probably won't. Oh. This also probably doesn't look very nice because I forgot to put enters everywhere. Yes, I do math. Okay, so we want to prove this. Then we need a base case, which is for n equals 0, or let me actually put that 4 outside of the math. And then we can copy this, but fill in 0. So
You mean 1 or 0?
1, excuse me. From 1 to 1 is equal to 1 times 1 plus 1 times 1 plus 2 over 3. And then we can copy that, and we can say, okay, the sum from 1 to 1, from I is 1 to 1 of this is just literally equal to the sum of 1 times 2, and this is 1 times 2 times 3. Now 1 times 2 times 3, 3 factorial, that's 6. So then we can say, okay, that is 1 times 2, that is 2, is equal to 6 over 3, that is also 2. So the base case holds. And let me look if it looks nice. For I is 1, Yep, looks good. The base case holds. Okay, then the induction hypothesis. We assume that okay, we want to prove if this is true, then n plus 1 n plus 1 n plus 2 n plus
We have
3.
to assume it for an arbitrary n, don't we?
Yeah, that's a very good point actually. For an arbitrary n greater than in natural numbers greater than or equal to 1. Oh, and I need to add an enter here. Okay, so induction hypothesis, we assume for an arbitrary n is part of capital N. Oh, I should probably say part of capital N, comma, n is bigger than or equal to 1. We assume that this, and we want to prove that if this, then this. Okay.
Wouldn't you write n plus 1 plus 1 or n plus 2 plus 1 to make it more clear what you're doing in the last one?
Yeah, we can do that. Sure. Okay. So we assume this to be true, and we want to prove this. So we take this, and we see if we can make it something that is always true, knowing that the left side is also true. Okay, so this is what we have. Let's simplify that a bit. So we'll,
Why do you write 1 plus 1 instead of 2?
yeah, I'm gonna do that. So I'll just say here, n plus 2, this is n plus 3. Okay, so now it looks a little bit nicer. And that's something we actually keep on our very tiny part of our screen. Then we can go on to the next part, which is saying, I do not want to use a package. Fuck off. We can say that this is equal to n plus 1 times n plus 2 plus this thing. And that is because, let me compile it, yeah, that is because we take this n plus 1, we fill it in here, and we take it outside of the summation. So then we have the sum of from I going, I is 1 to n of this thing, plus n plus 1 times n plus 2. And that's because we fill that in here. Okay, and now because of, and then we can say by the induction hypothesis, and we can copy this thing, but we can replace the summation with this. So we can say this summation is equal to this fraction. I forgot to copy a thing. If I don't copy one thing, it's going to complain. Okay, so now we have this. And we want to make it equal to this. Okay, well first let's add them both together so I can have a single fraction. So I can say the fraction of 3 times this whole thing over 3. And as you guys see in the step here, I'm just adding I'm adding 3 to the bottom and the top of this fraction.
You also could just factor it. Yeah, you could just factor it as n plus 1 times n plus 2, and just put n divided by 3 plus 1, and like, but okay. It's the same thing, so it doesn't matter, right?
Okay. So then I take this, then we combine these fractions into one single fraction. So I can take this part and say plus, I can say this part. So then we get this whole thing. Now I'm trying to look for, oh yeah, this actually worked great. So this is equal to saying 3 times this thing plus n times this thing. Because here we have n times that thing, and before that we had 3 times that thing. And that is the same thing as saying this, and then we can say n plus 3. Let me compile it, see where I've made a mistake. Yeah, because here we have n times this whole thing, here we have 3 times this whole thing, the same as saying n plus 3 times this whole thing, which we can rearrange to say n plus 1, n plus 2, n plus 3 is equal to n plus 1, n plus 2, n plus 3. So this holds. Which is what we wanted to prove. Therefore, by our proof by induction is finished, and we have proven that, oh shit, for all n greater than 1 n in n, and then we add a little box thing here.
It's probably a good idea also to say that this holds because it's for an arbitrary n, because there are dicks about that.
Wait, what do you say?
That is probably a good idea to say that this holds because the n was arbitrarily chosen, because there are dicks about that.
Yeah. N was arbitrarily chosen. Therefore, our proof by induction is finished, and we have proven that thing. And then we have a little. Where's my box? There we go. There's my box. There we go, boys. Okay. We're almost there. We're only busy for almost 2 hours. I mean, genuinely, we're well on pace.
How long is the exam itself?
3
Just
hours.
3 hours.
So we would still have like 2 hours or 1 hour and 15 minutes for this question, this question, this question, and this question.
And for typing them, because we don't have multiple choice.
Hmm?
Do we have multiple choice for R and L?
No.
He said no.
Yeah, so we have to write all the other ones.
Yeah, but then we would also get less questions. Because he also has to take into account that we have to write stuff.
Yeah, still, I
like
think
like
hope
CO
so.
did for the midterm.
Yeah. On the papers, everything, I think it's easier, man. But
Okay.
because I'm slow typer.
B. Prove the invariant that the invariant holds before the loop starts. Okay. Let me yoink this summation real quick. Because I CBA to type it out again. So we have the summation of I is 0 to 0 of I. And we can say that is equal to x. So x is... and therefore we can say x equals to just 0. Which is true. And that is because, if you do a summation from I 0 to 0, you just, don't really do anything. Oh boy, this is B1. So then we do B2. Prove that the invariant holds after an iteration, assuming it holds before the loop. Fuck, clicked in the wrong window. We know it holds before the loop, so x is equal to. So we know that this thing is true. But then going from 1 to C. And then once we add the thing, we after the loop, we know we see that it is x becomes x plus c, and we see that this becomes c plus 1. Well, okay, then we can say, because this is a summation of I from 0 to c plus 1 of I. That means we can get c plus 1 out of here. So we can say c plus 1. Oh wait, we're adding the new c. So this is c plus 1. Yeah, and we know that this is x. Oh, and we should put a plus here. Plus x, which is correct. And so we know we assume it holds before the loop, so we can use this interchangeably within our proof. And after the loop, x will be increased by c plus 1, and c will be increased by 1. So then we take out the c plus 1, we replace the whole thing by x, and then we have x plus c plus 1 and x plus c plus 1. Okay. And then we start looking at the next one, that is 3. Explain why the loop terminates, explain it at most 3 lines. So 3. N is a finite number. C starts at 0 and always grows. So at some point C will be bigger than N. There we go. Cool. Next line. Next question. 24. Below are 2 claims over sets. One of the claims is true and a proof for that claim can earn you 6 points. One of the claims is false and a counterexample including a clear explanation for that claim can earn you 4 points. Correctly indicating which one is true and which one is false gets you an additional 1 point for a total of 11 points for the question. Clearly indicate which one is you believe to be true. Okay, so here we have A is a proper subset of B, and B and C share at least one element, then A and C share at least one element. And also we have here that the A XOR B, so the symmetric difference of A and B, and you do that whole thing, union, no, intersection, C, then you get the symmetric difference, of A union C XOR B union C.
Intersection again.
Intersection. Um, okay. This seems like it would make sense by distributive law, but it also kind of seems like it would make sense.
No, the second one's false.
Hmm?
The second one's false.
Is it?
And why do you think so?
If B and C have an intersection that's not part of A,
Yeah?
then A and C don't necessarily have an intersection.
Mm. Yeah, okay, that's... yeah. A is a proper subset of B and C. B and C have at least one element in their intersection.
Oh yeah, you're right.
Yeah, it doesn't necessarily... yeah, okay, true.
Because of yeah.
So we have to give a counterexample for B. So let's
So
start with
it-
that. That seems easiest. B is not true with as counterexample. Yeah? Okay. With a counterexample. Okay, well, let's create some sets A, B, and C. Okay, so we want to have something that A and C are disjoint, and
1, 2, and then 2.
so 1, 2, and then 2.
No, B should be 1, 2.
Yeah.
So like this.
Yeah.
Yeah.
Okay, let's see. So A is a proper subset of B, correct. B and C share at least one element, correct. And A and C do not share an element. Okay,
Yeah.
cool. Alright.
That's already 5 points. Nice.
Yeah, we in these. And now for A. And this is just gonna be a direct proof. So we're gonna just write everything in predicate form. So we have x. So let's first open a bracket, and we want to go from the left side to the right side. So let's see, we have x in B, A O plus x in B. What it is, I'll come back to. And then we have the cap C. Or cap x in C. Oh wait, this shouldn't be a cap, it should be an or. It shouldn't be an or, it should be an and. Oh my god, I'm bad. Okay. So we have x is part of A, XOR x is part of B, and x is part of C. And we want that to prove that x part of A, XOR x part of B. So in an ideal world, we would just be able to use distributive law, but we cannot do that because this is not an and or an or. But we can try how far we come. So a proper definition of XOR shall be, let's see, A XOR B is not A or B, and not B or A. Is that correct?
Yeah, that's correct. You could
Well-
also write it as A or B, and it is not true that A and B.
Hmm?
You can also write it as A or B, and not A and B.
Oh yeah, so we can say A or B, A, yeah, or B, and not A and B. Yeah, that makes sense, because it's an exclusive or, so it has to be or and not and.
Yeah.
Okay, that makes sense, cool. So we're gonna copy this, and we're gonna say that X is in A, or X is in B. Oh, or X is in B, and not X in A and X in.
Shouldn't
In.
it be neg instead of
Yeah.
not?
Oh yeah,
Yeah.
yeah. And then we have two closing brackets. Now we end up with X is in A or X is in B, and X is not in A and B, and X is in C. Okay. So let me first get rid of that negation. So this will be not X and B, or not neg. Yeah, okay. So A or B has to be false, and not A or not B has to be false. Let me actually write it in a little bit more proper way. Let's do A not in, because that way you can better understand what is going on. Okay, so X part of A or X part of B, and X is not part of A or X not part of B. Okay. And now we do this whole thing times C. Let's see. So we have something in the form of. Oh, these are just three ands, right? Hmm.
Yeah, there.
So how can we include this C into one of these?
Distributive law, maybe? I don't know.
Yeah, but that would be if like this was an or sign. Hmm.
I guess we could also try to rewrite the right expression as well.
Yeah, that's true.
Maybe that would make it easier than trying to get into XOR.
Yeah, sure. So we'll take the right expression, which is X. Let's see, X in A and X in C. O plus X in B and X in C. And then we use the same definition for XOR. So that is A and or B what do you mean? Okay. So we have this whole thing and not this whole thing, but with and. And this is and. If you don't know what's going on here, it looks hella messy. At least on the left side it does. Okay, let me add a few more new lines. Okay, so now we have, for the new line, we have x is part of A and x is part of C, or x part of B, x or x part of B and x part of C. So we have first part or second part, and not first part and second part. Okay.
That's hella messy.
Fucking mess, man. Jesus Christ. This is not pretty, let me tell you that.
Yeah.
Couldn't we group the first ones as x is part of A or x is part of B and x is part of C? Like the first two groups as parentheses.
Wait, which one?
The like for the second part,
Oh, the second part? Yeah.
when we yeah, the first two parentheses. First two groups.
Yeah, these two.
Yeah, could we not rewrite this as x is part of A or x is part of B and then x is part of C?
Yeah, with the reverse of the distributive law.
Yeah.
Yeah.
Let's try that, see if that helps. So we take this and x and c, we take that out. So then we get this x in b. Okay, and x in c. So now we have x in a or x in b and x in c, or not x in a and x in v and okay. Let's see, this is in D and F, right? No, this is in C and F.
Yeah.
Okay.
Both of them are in CNF, right? No, not really.
No, this one is in C and F. And if we can get this one to C and F,
Which we can if you use the negation that we have.
yeah. But if we use this negation, then this is going to turn into an OR.
Yeah, so it will be in CNF.
Hmm?
Mm.
Oh,
So
and then
that-
maybe we could...
Oh, no. Yeah, it will be in CNF because you will also negate like the nested conjunctions.
Okay, we'll see how far we can get. So first of all, let me get away with some brackets here, because this is just an and. So now we have x is part of A or x part of B, and x part of C, and... Oh, need another bracket gone. And not this whole thing. Well, let's distribute this negative sign then, or this negation sign. So that will be the negation of the first thing, or the negation of the second thing. Okay, so so far we're still correct. Yeah, seems correct. Then we copy this thing. And then we have the negation of the first thing, which will become x not in A, or x not in C. And this will become an and this will... No, it won't.
No, you don't.
I was about to say, we already swapped that sign. And this one becomes x not in B, or x not in C. Okay, let me see if that's correct.
Yeah.
So we start with this, then we distribute this sign, that seems right, then we distribute this sign, and that also seems correct.
And we can also simplify that because
Yeah.
x.
Because this
Yeah.
can be x is not part of A, or x not part of B, or x not part of C.
Yeah.
Oh shit. So then I can take away this part until here, and I can take away this bracket. and then I can take away one set of brackets here.
Yeah. And then since we have as one of the elements of the conjunction that x is part of C, then we can remove x isn't. Yeah.
Yep. That's a good one. This is a really good training because I haven't done this in like months.
Yeah.
So we can take away this part because this will never be true. So this is the same as saying or false, which is just the same as saying x. So now we have Jesus fuck. Guys, I think we've done it.
Same.
Yeah, we have
Yeah.
the same.
I think we've done it. Holy shit. Nice. So I can take away this and replace it here. Or well, let's do that afterwards. Let's add one more line just to reorganize things. And say this and goes here. Okay, and then we can we beforehand say we can rewrite the first part as, and then a new line. We can rewrite the second part as. Come in.
Nice.
Wat? Vent?
Ja.
Of een ventilatoren?
Ja.
Waarom?
Ik wil er eentje aan de bovenkant zetten, zodat ik extra airflow heb. Ik heb nu eentje aan de achterkant die air eruit trekt, maar ik heb één inflow fan die hieronder zit.
I don't have any computer fans lying around. I'm sorry. You should ask Gil.
Dat was mijn second option.
Okay, you. And therefore we can see that these two statements are the same. Which is what we wanted to prove. And then really satisfying, we put a little box there. Okay. Okay, so let's see, we can write the first part as being this thing. We can write the second part as a lot of work being this thing, which is literally the same thing, and we can see, therefore, we see these two statements are the same, and that's what we wanted to prove. Okay. Yeah, okay, cool. That's 11 points. 2 more questions, guys. We only have... Oh, we still have like a full hour. Okay, 25. Given the recursive definition of set A that only contains the number 120 and the number and for any numbers in the set also contains all the factors like divisors of those numbers and all of the products of those numbers. What?
Can you scroll a bit to the right? Okay.
Oh, we need to give a recursive definition. Like, what? That doesn't make sense.
Yeah.
We just don't have to worry about if it makes sense or not. We just have to define it.
Yeah.
Okay, so 25. A. Let me add some more new lines. A. New line. 1. 120 is in S. And let me add little neat things around that. Okay. 2. If there exists two numbers x comma y so that x m dot y is equal to x.
Where
Or-
do you write the exists here?
What did you say?
Where do you write the exists here? I don't think it's necessary.
Okay, that's true. We can just say if x y is equal to z in S, right arrow. This should be a C dot, my bad. Right arrow x comma y in S. Or
Do
let's
we
do
have
this in
to
another way.
write
Let's
all
say
the divisibles?
if c times yeah. So if x times y equals z and z is in S, then x and y are in S. Oh, where am I? Okay. So this is all the factors of those numbers. And I think factors and divisors are synonymous. But because this is an open book exam, we can say difference between
They're all
factors.
the same. They're the same.
Hmm?
They're the same, yeah.
A factor is a divisor that divides the number entirely, leaves no remaining. Oh yeah. So any number can be a divisor, but because we work in the world of n, we assume we work in the world of n. Yeah. Let's just say they're the same. And all the products of those numbers. So we can say, let me add another new line. If x and y, or actually let's say x comma y in z, or in S, right arrow x c dot y in S. And let's see if this looks correct. If x and y are in S, then the product of those numbers are also in S. Okay, and then let's say for there is nothing else in S. Very important, don't forget that. Okay, and then for B, we have to prove that the recursive definition, each word in S contains an odd number of A's. Okay, we're going to use structural induction. We define a function f of x that takes in a word x and returns a the amount of A's in that word. To prove if x is a part of S, then f of x. Wait, is it odd or even? Odd number of A's. So then, okay, we can let me say n mid 2. Okay, we have function f of x that takes in a word x and returns the amount of things that work. So if x is in f, then the number of A's in x is not divisible by 2. So that's correct. Okay, and now we have to prove that. Okay, we will use a proof by structural induction.
Wait, I have to interrupt. The divisible by 2 is like, isn't it like 2 does not divide?
Yes, I messed it up always. I'm gonna mess it up on my test as well. So 2 does not divide f of x. Yeah, that seems a lot more logical.
Okay.
Thank you. Okay. We will use a proof by induction. By structural induction. Base case x in S. Okay, so we insert that into our formula. So we say f of x is equal to f of... Good. Yeah, f of x, let's just do that. And that is equal to 0 because there are... I was looking at this one, I should be looking at this one. A is an f. F of A is equal to 1, which is odd, and therefore the base case holds. Induction hypothesis. So we say x is in S and x, f of x, or and 2 does not divide f of x, then how do we say this? So I'm currently at the part of the induction hypothesis. Wait. Hmm?
Are you sure what you're trying to do now is the induction hypothesis and not the induction step?
Yeah, I'm probably doing it wrong. Let's look at induction, what's it called again? Step induction? Structural induction. Structural induction. Okay, give me one of those. Structural induction. Okay, so the oh wait, what? They don't have an induction hypothesis?
Because the induction hypothesis is like the left part of the implication, basically.
Yeah, true. So I'm only going to define an induction hypothesis, namely that if x is in S, then we assume this is true for some arbitrary x in S. Inductive step 1. Okay, so now we go back to the inductive step 1, which is the fuck? So this one. X in S, right arrow, xi in S. We know that since x in S, f of x is equal to 2y plus 1 for some integer y. F of, what was it, xy is equal to f of x plus f of I is equal to 2m plus 1, 2y plus 1 plus 0 is equal to 2y plus 1, which is odd, which is what we wanted to prove. Yoink. Induct step 2. If x is in I, then AXA is in S. Okay, so we say AXA is equal to f of A plus f of x plus f of A, which is 1 plus 1, which is 2 times y plus 1 plus 1, which is odd, which is what we wanted to prove. I make really long sentences. But let me look at if it's correct. Let me add another. We add another backslash. Okay, so The inductive step 1, if x is in S, then xy is in S. We know that since x is in S, f of x equals 2y plus 1 for some integer y. F of x, y, xi is equal to f of x plus f of I, because, you know, the number of a's in xy is equal to the number of a's in x plus the number of x and y, a's in y. Then we plug that in, we get this, which is odd, which is what we wanted to prove. Okay. Second one, same thing. Okay, next step. What else is in the thing? Also, y, x, y, x, y, x, y, y, I. I hate that I pronounce x, y, and I the same way. I'm sorry if this is confusing for you guys. Okay, so then the last part is the is just, or is that the last part? Yeah. Inductive step 3. If x is in x, comma y is in S, then y x I x I is in S. Okay, so we have f of I x I y I x I is equal to okay. And since we have proven this all for some arbitrary element x in S, this concludes our proof by structural induction, and we have proven that. What do you want to prove again? If x is in S, then the number of a in x is odd. Cute little box. Okay, one more question, guys. Come on, we're almost there. Okay, so describe in your own words 2 differences between functions and relations.
Where do you think they got that image from?
Ooh, good question. I think it's probably from Hentai Haven. Okay, 26.
Why is it down again?
Ah, 26a. Describe in your own words the difference between functions and relations in the most 5 lines. Relation. Or a
function can be a relation, but a relation doesn't have to be a function.
Function or relate. Oh yeah, they explained it in some weird way. Never mind. Not gonna look into the document then. That's a good point. That's one of the difference. Every function is a relation, but not every relation is a function. For example, f of x equals to, and then we look for the plus or minus symbol latex slash pm of x is a function and is a relation but not a function. This is because relations can have because
We're getting close to 5 lines. I think we're getting close to 5 lines.
Not really. This is one line. This is one line. We're currently on line 3.
Yeah. It's small.
I just make really long sentences.
Yeah.
This is because functions are because functions can only have one output per input, while relations do not have that constraint. Yeah, okay. B. For each of the following functions slash relations, indicate if they have an inverse. If so, give it. If not, explain why not. The f of x is equal to 18x.
Difference.
Hmm?
Is this 2 differences between relations and functions?
I gave one function that one difference that every relation is a function and not the other way around. I gave one difference that functions can only have one input and relations do not have that constraint.
Yeah, but they say we should have 2 differences, I think.
Yeah, well, one is that like this, and the other one is that this.
Wait, are they not the same?
I mean, I guess. Like, what else? What other difference would we pick?
I don't know. That's why I'm asking.
Yeah. I just said, like, every function is a relation, but not every relationship is a function. That would be a difference. And that every function can only have one output, but the relations do not have that constraint.
But is that first one just not saying from like they are different, but nothing else? You don't really say a difference. You just say they are.
Yeah.
Different.
Okay. I guess that's like not quite giving a concrete difference. Anyone else thinks of can think of another difference?
I thought like functions only have like a binary relation, I think, and relations can have an array relation where n is a positive integer or something.
I don't think that's true because we can have the function f of x comma y is equal to x plus y.
Okay.
That would be a function.
Functions are generally mathematically defined, whereas relations can just be real-world relations.
I mean, that doesn't have to be true. Because, like, if you look at the function at 4, that is just a normal function. That's just the function f(x) is x.
Huh?
If you look at the function at 4, like b4, that is a proper...
Yeah, that's a function and a relation because functions are also relations.
Yeah, exactly.
Yeah,
but it's not mathematically defined. So that's not a good difference.
No, relations don't have to be.
Yeah, but neither do functions.
Right.
Because that bottom one is a function, but it's not mathematically defined. It's just that we often use functions in math, but it doesn't have to be used in math. For example, there is a function of, I think it's like half mother. That's not a mathematically defined function, but it is a function. I'm gonna go back to the book, see if there's...
Point.
Hmm?
Rip 1 point.
Should we just take the L? Okay.
Well, do we have the answers? Because we could look there after the test.
Oh yeah, I think we do have the answers. So we won't take the L. We'll just say, oh, we didn't know, but now we do. So we will take this, and then for B we have yes, namely if we have y. I'm just gonna write it into the terms of x and y real quick. Y is equals to 18x plus 26. Yeah. Y minus 26 equal to 18x. X is equal to a fraction of y minus 26 over 18. So we can say the inverse, wait, if they have an inverse, give it, if not, explain why not. This one does, namely, and then I can say the inverse is just filling in x for y and y for x. So f of x equals to this fraction. Okay, what about 2? And this only works because they are both
Objective.
Because it's bijective.
hmm?
Because it's bijective, right?
Yeah.
Yeah. Yeah. Um Hmm.
Like it's not
It
bijective.
doesn't have
right?
it doesn't have an inverse.
No, because the inverse wouldn't be a function, and it's not.
In the lecture we were talking about like that
Well,
the inverse needs to be a bijection, right? It needs to be a bijection to have an inverse, and because
Yeah.
the cardinality is not the same,
yeah, this isn't injective because yeah.
Yeah, because as soon as you can say the cardinality is not the same,
then it's not bijection.
Yeah.
And therefore, there's no.
no, the cardinality.
One is
the-
countable and the other's uncountable.
Yeah. Cardinal. Fuck this side. And are different. They are not bijective, and therefore they do not have an inverse. 3. Sure. Namely, H. I'm gonna say H. Opening. Is equal to, so the inverse of H is equal to B comma A, D comma C, F comma E, G comma H, J comma I. That's not correct, I made a typo. It should be H comma G. And then here, let's see. Yeah, it will not properly show the these brackets because they are termed in LaTeX, so I can do this and then they will properly show up. So we can say the inverse of H
Maybe
is equal to this stuff. Hmm?
maybe also add the parentheses with the argument or not. Oh no, you don't.
No, because there, yeah, it's just a binary. It's just a relation.
Yeah.
So then we have 4, and that is sure, namely, yoink. The inverse of L is equal to 1, 1, 2, 2,
Say it itself.
3, 3.
So it's the same function.
Yep.
Wow.
This is a function whose inverse is the same as the original function. Because if you were to like mapped it out mathematically, you would have the line f of x equals to x, and the inverse of this is just, yeah,
Yeah.
But if the inverse is itself, is it really an inverse?
yeah,
Yeah,
yeah, definitely. Okay, the last answer. Holy shit, we're almost there. I was really afraid. I thought we were gonna like look at this, but I don't. Ooh, wait. Damn it, I spoke too soon. This one actually has a thing. Fuck.
You jinxed it.
I thought it was like, oh yeah, look at this, but it's not actually a thing. But actually, it is a thing. So if we look at C3, I hate the fact that exams are like 26 C1. Okay. Out of the following two relations, one is an equivalence relation and the other is not. For the relation that is not an equivalent relation, give a counterexample as an explanation of why it is not at the most 5 line for 2 points. For the relation that is an equivalent relation, explain why it is. It's because all the properties an equivalent relation should have, and at most 8 lines for 3 points. We are genuinely almost running out of time. We have 25 minutes for one thing. It's not too bad. Let x and y as r for some triangles x and y, if and only x and y are similar triangles. B. A relation B over people. Let A be a person x, have an age of ax and hourly wage of wx. Then, let x and y is part of B for some people x and y, if and only if the sum of the wages is less than or equal to the sum of their age. What? Okay. So, similar relationships have to be reflexive, transitive, equivalence relation, not similar relation. Equivalent relations have to be reflexive, transitive, and symmetric. So for this one, they are both transitive or symmetric, because if this is a similar triangle to this, then this is a similar triangle to this. Okay, yeah. So this is similar to this, and this is similar to this. So it's that. And for a person, let's say they have a wage of 3 and so let's say it's like 3 and 0, and the other person has 2 and 3. So this would mean that 5. Wait. Is there like no way this will be correct, right? So 5 is strictly less than 3, which is alright. And oh yeah, because if you swap them two around, it's still 5 is strictly less than equal to 3. Okay, so they both are reflexive or symmetric. Sorry, I got a message from my girlfriend. Okay. So let's see. The second thing is transitive. Well, that makes sense for these again, because if this triangle and this triangle are similar, and this triangle is similar, then these two are also similar. So that makes sense. Let me look at the last one real quick. Yeah, it's also symmetric, because if this one is similar to that one, and that one is similar to this one. That's what I said. Oh yeah, and all triangles are also similar to themselves.
Yeah.
Okay, so we know for a fact that one is true.
Although we would have to prove it, right?
Yeah. But we can do that because we just did that in our head.
Yeah.
But we would indeed have to prove it. But 2 is false. But why is it false? Because we have to give a counterexample.
Well, it's pretty simple to prove that's not true.
And why is that? Can you give a
So
counterexample?
let's say we want to test if the relation is what was the name of reflexive. Then if we have child labor and we have a 5-year-old who earns let's say a wage of 10, then this won't be true, right? Oh wait, no, because oh yeah, I
Oh
guess.
yeah, that's true. So if we have person X with an age of 0 and a wage of 1. Wait, let's see. Suppose there is a person X with a age of 0 and a wage of 1 to be an equivalent relationship. B, A, comma A should be in B. Therefore, or let's say X, comma X should be in B. Therefore, 0, or no, let me turn these around. It's an age of 1 and a wage of 0. No, no, a wage of 1 and an age of... Oh, an age can't be 0, I guess. Because then they're just being born. Whatever, we'll take an age of 1 and a wage of 2. Therefore, 2 plus 2 is strictly less than or equal to...
Not strictly. Oh yeah, or equal to, yeah.
Yeah, okay, I should say either strictly less than or equal to, my bad. So it's less than or equal to 1 plus 1.
So
So
doesn't
4
that just
should
mean
be...
that they're not in B?
Hmm?
Doesn't that just mean they're not in B?
Ooh. Ooh!
Yeah,
B
but
consists of 2 people, right? If they So there
yeah,
there
but
can be
B is
one guy who earns like a lot for his age, and one guy who earns like nothing for his age or something like that.
Yeah, but...
Like, if,
Oh
like
wait, maybe it's
yeah.
like they are in the... Wait, fuck, it's a relation that's in B.
okay, but
Mm.
if
Okay, wait, that doesn't work.
if the relation is reflexive, then it should work. If you plug in XX, it should work for any person X.
No,
So
for any person X in B.
okay, but B is an example. I mean, B is a relation. So
Between
what do you
itself.
mean, every person in B?
Well, that means that, like, for example, say you have just this as a relation. We can't just say, okay, suppose number 3 and, like, I don't know, 4 and 5 and 3. Well, then it doesn't hold. Well, of course it doesn't hold, because that's not part of the relation. We know it's a
What?
relation A and B. We know that's the relation. We just have to prove that... Hmm.
No, but X and X is an
Yeah.
argument. It's not.
There can be someone else who earns like less than his age. Like
Oh
if
wait,
he
it's
is
not
like
symmetric.
15 years old and he earns $5 or something, and then if they combine, there is a relation between them. But if you say a reflexivity, then there's no reflexivity between the one
Yeah.
person. But
Wait, yeah, there can be a
yeah,
relation like with that baby with someone else who like, or that equation does
wait,
hold.
I'll have to open the door.
Okay,
But
but
so then they are in B,
One at a
but
time.
then it doesn't hold for itself, so it's not symmetric.
it's not reflexive.
It's also not symmetric.
Yeah.
Okay,
So
so let's see. So we have, suppose there's person X, and there is person Y with an age of 100 and a wage of... Wait, so the wages combined have to be less than,
Yeah, the weight is lower.
so the wage of 1. First we can deduce
I'm not.
X comma Y is in B because So both of the wages combined, so that is 1 plus 2 is strictly... Oh. Okay, that's not quite true yet. Because this is not strictly less than 101. Wait,
Why is it not?
I was about to say, wait, I'm dumb, this is correct. Because 3 is less than 101.
Yeah, so it's
To be in a equivalent relationship, X and X should also be in D. Therefore, this. However, this does not hold, so B is not an equivalent relationship. Alright guys, we did it. Now I need to prove that this is true. Let me add a few more enters.
Also, maybe add an enter after the 1.
Hmm?
Yeah, like that, yeah.
Yeah, but we're still not done with this one yet, so. X is true. A triangle is always similar to itself. If if triangle A is similar to triangle B and triangle B is similar to triangle C, then triangle A is similar to triangle C. And lastly, try and hey, that's correct.
Triangle.
Oh, I was like, huh? But it's missing now. And lastly, if triangle A is similar to triangle B, then triangle B is similar to triangle A. Similarity has all the properties of an equivalent relationship, and therefore it is an equivalent relationship.
Are you going to upload the text file, by the way?
Hmm?
Are you going to upload exam.tech, by the way?
Am I going to do what?
Are you going to share this this file you're writing in?
Oh, this one? Oh, yeah,
Yeah.
sure.
Okay. And where
Oh,
are you going to do that?
excusez-moi. Alright, what did you say?
Where are you going to put it?
I'm gonna put it in the description of this YouTube video I'm recording at this moment. I'm gonna be putting it as well as just in the channel.
Because maybe you could put it in like something like GitHub so that if there's any errors, people can correct it.
And I can put it where?
GitHub or something so that
Yeah,
people
yeah,
can...
it will be in GitHub.
Okay.
Yeah. Okay, so let's check them. I have a file on my thing here called Endterm 2 answers. For the people on YouTube, well, I was about to give a spoiler because like the answer is gonna be on the screen, but it should be pretty logical. But let's have a look. So we're only really gonna look at this part. Okay, so for the multiple choice part. Jesus Christ. Okay. We scroll up. A, that is correct. C, correct. Let me zoom in a bit more. Oh, zoom in a bit more. Yeah, I don't think we can zoom in a bit more than this.
You can do that thing to the side
Oh
in
yeah,
the
safe.
PDF viewer.
Good point. Then B is correct. A is correct. B is correct. Oh, also, I will note that we did it in 2 hours and 50 minutes. So for 6,
What's the time supposed to be?
3 hours. So we had 10 minutes to spare. And this is like with explaining everything and stuff, so. B is correct here, A is correct here, Here, exactly, B is a premise that we do not need, the argument is still valid. A is correct here. C is correct for 10. Yep. Then we have C correct for 11. C correct for 12. D correct for 13. C is correct for 14. B is correct for 15. B is correct for 16. B is correct for 17. C is correct for 18. D is correct for 19. I was already wondering about this one, but you can just do whatever. Oh, they just give examples for everything. Fucking madman. Yeah, this one is our little image, so that's good. Okay, and for the last one, open questions. Well, big ass fucking truth table. No, they differ. Okay, so we would have that one correct. Because they have a different value. Oh. So I'll find these two as correct because I assume you guys are smart enough to make truth tables. Then yeah.
Bold of you to assume.
Yep. The answer is literally just Q. Okay, cool. Yep, that was correct. 20. Take the structure A. Can I scroll down there? So D is 0 to 10, correct, 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 correct. And here they explicitly wanted... ooh! We forgot 10, 10. Did we? Yeah, we did. Oh my god, I'm dumb. So I would have one strike here.
Also, the brackets aren't showing.
Yeah, but that's just with...
Yeah.
It's a thing with LaTeX. Because if I'm doing LaTeX I want it to show brackets, I should theoretically put them between the dollar signs and escape the brackets, but I couldn't be asked because I wasn't doing LaTeX, I was doing RNL.
Yeah.
Okay. Maybe conclude. Yeah, there is an X for that X is 2. Yeah, that's what we said. So that's correct. Okay. Then the next part, proof. We do a proof by induction. Yeah, we show that. By the induction hypothesis, we put this in, they folded together. Yeah, that's exactly what we did. So that is all this. Okay, so this one is correct. Consider the following function. Yeah. Okay, prove the invariant holds. Well, x new is x old. Yeah, okay, we proved it the other way around, but I think this will still give us full points. So that is correct as well. Where it increases, it will be larger than n, which will terminate the loop. Yep, that's what we had. Okay, we, yeah, alternative proof for tooth. Yeah, like, this is just correct. Like, we've proven this. For 3 sets A, B, and C. Yeah, we, this is exactly the example we had. I don't know who created that, but good job. So that's also correct. And then for the last one, we say, at 120 is part of X. Oh, they did it in a different way. They say if X part of X, then if X part of A, then for all Y, if Y divides X, then X part of A. I don't know if we would get
Pretty
full
much
points for
the
this
same
one, so
thing,
I'm gonna
right?
deduct one more. Okay, so, and then we have nothing else. Yep, yep. And this one is correct. Okay. Define the definition fx. Hey, they also did that. Woo! Um, okay. We base case to correct. Inductive step. Is there like... Okay, no. Yep. 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 Yeah, we had all of that correct, so that would be full points as well. And this is 26. Yeah, this is what we had as well. We get the plus and minus. They have it. Yep, that's correct. Ooh. Oh yeah, this we said they do not have. Yeah, and alternatively mention that the cardinality is different. That's what we did. Well, we did this as well, and we did this as well. Okay, and then the last one. Yep. Okay, I was really confused about this, but like they mean brackets around here, but we did that as well. Okay.
Oh, they did child labor as well.
Oh yes, child neighbor Pog. And we had an example as well, which is just good. Okay, so in total we would have 2 mistakes.
What were the mistakes, by the way?
Hmm?
What were the mistakes?
Let's see, we had... where is it? I think they were like very small mistakes. Like nothing in these ones yet. And then as soon as the open questions came, we had a mistake here because we didn't add 10, 10. But that's just, yeah. That just, it happens. We had this one was correct. We did it like the other way around here.
Mm-hmm.
So I even though I guess, you know, it wouldn't make, it wouldn't
Yeah.
be too bad, but I still, you know, I wanted to be conservative.
Yeah.
Um,
Pretty damn good.
yeah. Here we have, here it says if x is equal y, then for all y divides x, then y is an a. We did it the other way around. We said for all x and y, if x and y, x times y equals z, then x and y are an a. I'm not sure if that's the same, but I just like gave us one mistake just to be sure.
Okay.
And this one is just mostly the same as well.
Difference between functions and relations. What's the answer for it?
In a relationship, we can map a single object and domain to multiple objects in a range that is not allowed in a well-defined function. That's one.
So they got it wrong themselves.
Yeah, they would get 1 point. We got
Nice.
2. This one is correct, this one is correct, and we had these 2 correct as well. Yeah, so that's it, those 2.
Nice.
Yeah, now let's check. So we had 2 mistakes, both concerning 1 point each. So the max of gag. So let me grab a little bit of Python. Python 3, of course. So we have the multiple choice, and p is equal to 1 plus 9 times, and we already know we have more than that. So we had full points for the multiple choice. How many points? It does not say how many points we get for multiple choice. Do we seriously have to count that?
It doesn't matter if we have full. It's just a 10.
Oh yeah, okay, that's fair. So, oh, I think it would be 20 in this case. So that is...
Is it?
Hmm?
Is it 20 questions?
20
think
points in total, I think
Right
so.
before it says, yeah, like the first point says the exam consists of 20 multiple choice.
Yeah, because like if this is 20, then it's 1 minus, so that's 75. So this will be a 10. Or at least a 1.0. So, you know, it does make sense if there's more than that, because then you can get an 11, and it doesn't make sense if there's less than that, because that would mean you get an, you would at max only be able to get a 9.6 or whatever. So this is just 1 plus 9, so this is just a 10. Open questions is 1, open question is 1 plus 9 times. The score we had was about, let's say, 64, or let's say 62 to be conservative. So this is what we already had at least. Divided by 66. So, and then the question is, full point is equal to 0.4 times MC, multiple choice questions, time plus 0.6 times open questions. What is the mark we got? A 9.7.
Nice.
We take those.
Damn, that sucks. Way better.
No, we
Not
could have done
the
so
shit.
much better.
Not the
SMH.
10.
Pretty shit.
L.
L, we take the L, boys.
And that's even being hard on ourselves for that one question.
Yeah, exactly. Like if we got like only 2 mistakes, and we probably didn't even get to, but you know, to assume we only got 2 mistakes, yeah, we'll give it a 9.8.
Still not a 10. Kind of bad.
Well, what happens if we only get 1 mistake? Would it be rounded to a 10? Let's see. It wouldn't be rounded to a 10. Sad. Alright, that is the end of the first part. So for YouTube, that's going to be the end of the video. There's another video on my channel about doing a CO exam. For the people in my live stream, I'm going to do that now. For the people in the YouTube, you can find that video somewhere on my channel. Good luck. Have a nice day.